Hello, welcome back. This is the continuation of the lecture on the topic independence of the path of the contour integral. Definition, antiderivative. We already discussed this definition of antiderivative in the case of real variables. So here in the complex variable, functions of complex variable, suppose f is continuous in a domain D if there exists a function capital F such that f dash of z is equal to small f of z for each z in D, then capital F is called the antiderivative of small f. That is, if antiderivative is actually we know it is the integral actually. So if small f of z is continuous in a domain D, then if there exists a function capital F such that f dash of z is equal to f of z, then we can say that it is for each z in D, then we can say that this capital F is the antiderivative of f, and we can represent that integral f of z dz is equal to capital F of z, right? Okay, in that case. So we know that if f is an antiderivative, then f of z plus c is also another antiderivative. It is the most common form of the antiderivatives because where c is a complex constant. Okay, so we this is as in the case of functions of real variables. Now we have the fundamental theorem for contour integrals. Fundamental theorem. Fundamental theorem for contour integrals. This is also as in the case of functions of real variables. Here the theorem states that suppose f is continuous in a domain D and capital F is an antiderivative of small f, in the domain D, then for any contour C in D with initial point z0 and terminal point z1, we have integral over C f of z dz is nothing but actually we are given that small f is continuous in a domain D and capital F is an antiderivative of this small f. So capital F is an antiderivative of small f. Then we already know in the case of real variable, functions of real variable, we have integral a to b f of x dx is nothing but f of b minus f of a, where capital F is the antiderivative of small f. Similarly, in this case, for any contour C in D with initial point z0 and terminal point z1, we have contour integral over C f of z dz is nothing but capital F of z1 minus f of z0. Okay, this is because integral of f of z is capital F of z. So applying these limits, f of z1 minus f of z1. We can prove this fundamental theorem in the case when C is a smooth curve. Okay, if C is a smooth curve defined by z is equal to z of t for a less than or equal to t less than or equal to b. So we are C has the terminal point z1 and initial point z0. So we have C is defined by this curve z equal to z of t for t varies from a to b. Therefore, at t equal to a, we have z of a is nothing but z naught. Z naught is actually z of a, and z of b is equal to z1, right? Okay, this is the terminal point is when t equal to a, and sorry, the initial point is when t equal to a, and the terminal point is when t equal to b. Okay, so we have z of a is z naught, and z of b is z1. Clear? So we have we suppose that f is continuous and capital F is an antiderivative. Since capital F is an antiderivative of small f, we have what? Capital F dash of z is equal to f of z for all z belongs to D. Clear? We know that. Now we have integral over C f of z dz. By the definition of the contour integral, we have integral from t equal to a to b, t equal to a to b, that is t from a to b, f of z of t into z dash of t dt. This is the definition of the contour integral. Okay, but we have f of z can be replaced by f dash of z. So capital F dash of z. So we have integral a to b capital uh, uh, f dash of z of t into z dash of t dt. We can write this as. Okay, so this is nothing but by chain rule we know this is integral a to b f dash of z of t into z dash of t is nothing but derivative of d by dt of capital F of z of t. By chain rule we know that uh, uh, d by dt of f of z of t is nothing but f dash of z of t into derivative of z of t, that is z dash of t. So we can replace this by this. Okay, by chain rule. So this is actually integral a to b d by dt of this is nothing but integral f of z of t. Okay, f of z of t from a to b. So this is equal to f of z of b minus f of z of a. But we know that f z of b is z1. Actually, this is the terminal point z of b equal to z1 and z of a equal to z0. So we have this is nothing but f of z1 minus f of z0. So the integral over c f of z dz is nothing but f of z1 minus f of z. That is what is the fundamental theorem for contour integrals. So now we can just use this theorem to find the integral in the previous example. Actually, we have the example here. Evaluate integral over c f of z 2z dz. So we have used here this was our c. So we instead of this c we taken this c1. Okay, for convenience. But here we know 2 it was because 2z is analytic. Okay, so in this case we need to integrate this f of z, that is 2z over c from z is equal to -1 to z equal to -1 plus I. So we can directly integrate this. So we need to integral uh, that example 1. Okay, so we have to find the integral over c f of z is actually 2z dz from z is equal to -1 to z is equal to -1 plus I. Okay, so since f of z is equal to 2z is analytic, and by using the fundamental theorem we can write directly that integral over c to z dz is equal to, so integral of 2z is nothing but 2z square by 2 from z is equal to -1 to -1 plus I. So we have here C is a curve from -1 to 1 plus -1 plus I. So directly we can integrate. So this is nothing but z square from z is equal to -1 to -1 plus I. So this is by using fundamental theorem. Okay. So this is z square, this minus 1 plus I whole square minus minus 1 square. So this is equal to minus 1 square is minus 1 plus I square is 1 plus I square minus 2I, here minus 1. So this is nothing but I square minus 2I is minus 1 minus 2I. So simply we can do like this if this integrand is analytic. That means this if integrand is analytic, we know this in contour integral is independent of the path of C, path C. That means contour integral depends only on the endpoints. Clear? Okay. Next we can discuss another example. Evaluate integral over C cos Z dz, where C is any contour with initial point Z equals 0 and terminal point Z is equal to 2 plus I. So here also we have the function f of Z is cos Z. So cos Z is analytic. F of Z is equal to cos Z is analytic everywhere in the compass plane. So we have integral over C cos Z dz is nothing but integral from Z is equal to 0 to 2 plus I cos Z dz, which is nothing but integral of cos Z is nothing but sin Z from 0 to 2 plus I. So we'll have this is nothing but sin 2 plus I minus sin 0. We have sin 0 is 0. So this is sin 2 plus I. If we want to write this in the form of a plus ib, we have sin 2 cos h1 plus I into cos h or cos 2 sin h1. Okay, separating the real and imaginary parts. So this will be you can just find by using your calculator. It will be 1.4031 minus 0.4891 I. Okay, so we can directly find since here the cos is analytic, we can directly integrate the function and we can use the fundamental theorem. Okay, next we have a theorem. Existence of an antiderivative. Existence of an antiderivative. Okay. This theorem states that if f is analytic in a simply connected domain D, then f has an antiderivative in D. That is, there exists a function capital F such that f dash of z is equal to f of z for all z in D. So that is the existence of the antiderivative. So that is if f is analytic in a simply connected domain D. Suppose we have a simply connected domain D and in this D, if f is analytic, okay, then f has an antiderivative in D. That means there exists a function f such that f dash of z is equal to so small f of z for all z in this D. Okay, that is the existence of an antiderivative. Okay, so we can do a problem here. Evaluate integral over C 1 by Z dz, where C is the contour shown in the figure. So this figure is actually let this be the C. Okay, this point is 3, this point is 2i. Okay, this is y and this is x. So we need to find one integral over this C 1 by z dz. Okay, so C the we have the initial point of C is 3 and the terminal point of C is 2i. So what is the can we apply the fundamental theorem here? So here we know what is the antiderivative of 1 by z. Actually, we know 1 by z is analytic at all points of the complex plane except at the point z equal to 0. Except at the point z equal to 0, this 1 by z is analytic. So if we exclude this point, then we'll get an antiderivative for this 1 by z, that will be ln of z. Okay, we have ln of z is the antiderivative of 1 by z if we excluding this point. Also we know that ln of z is not defined the points uh, in the negative real axis and non-negative non-positive real axis, and this point also and 0 also, and this point this. So this is what is the branch cut. We know the branch cut of the principal branch of the logarithm. Okay, so uh, here our curve is C, it is from 3 to 2i, and this is our curve now. Okay, so we know so we have to take a region or domain. On that domain, in that domain, ln z and 1 by z are analytic. Okay, so we can take such domain, we can take this region. That means x is greater than 0 and y is greater than 0. X is the real z. So we can simply define the simply connected region. Suppose D is the simply connected region or simply connected domain defined by uh, x is greater than 0, or x equal to what is x, a real part of z which is greater than 0, and y is also greater than 0, y is imaginary part of z which is also greater than 0. That is the first quadrant actually, this region, or this let D be the domain D defined by this x greater than 0 and y greater than 0. So we know on this domain D, or in this domain D, we have both 1 by z and ln z are analytic. Okay, therefore in D both 1 by z and ln z are analytic. Okay, therefore we have ln z is an antiderivative of 1 by z. Okay, therefore in D ln z is an antiderivative of 1 by z. So we have the integral, we can use the fundamental theorem for contour integral, integral over C f of z dz. Here f of z is actually on integral over C 1 by z dz is nothing but the antiderivative is ln z from the points are 0, 3 to 2i. Okay, 3 to 2i. So we have, this is nothing but ln 2i minus ln 2i minus ln 3. So this is equal to, we know ln 2i is equal to log of mod 2i plus I into argument of 2i Argument of 2i is actually 2i is pi by 2, right? This is because 2i is, this argument is this is 2i, the point 2i, so this is actually pi by 2. Okay, so minus ln3, we know ln3 is log of mod 3 plus I into argument of 3. Argument of 3 is 0 here. Okay, this is 0 into 0. So this is nothing but log of 2 or mod 2 is log 2 plus I pi by 2 minus log 3. So log 2 minus log 3 is equal to log of 2 by 3 plus I into pi by 2. So finding this value, we have minus 0.4055 plus 1.5708 into I. Okay,